Okay, this will be the lecture for Chapter 20, and we're talking about sound a little bit more. We're going to talk about musical sound and kind of the difference between noise and music, as subjective as that is. I'll talk about kind of the properties of musical sounds. I'm going to talk about pitch, I'm going to talk about loudness, I'm going to talk about quality. I'll talk about some stringed instruments and some wind instruments and how those guys kind of work. I'll talk about Fourier analysis, which is how we can add together musical sounds or subtract them out if you want. And lastly, I'll talk about how we can go ahead and we can record sounds. So first of all, let's talk about what is noise. And noise is not going to have any given frequency associated with it. Music will. So it's going to be some irregular vibration of the eardrum by a whole bunch of different frequencies and wavelengths and amplitudes all added together. And essentially, if it looks pretty, it's going to sound pretty. If it doesn't look pretty, it's not going to sound pretty. So this could be the pressure of air against your eardrum as a function of time, and that doesn't look pretty, so there's a really good chance that this is going to look a whole awful lot like noise. Now, music, on the other hand, is going to look pretty, and it's going to sound pretty as well. It's going to have a periodic tone or a frequency associated with it. And bear in mind that music and noise can be kind of a subjective difference. What sounds good to me might not sound good to you, and vice versa. But in general, music is going to have some fundamental frequency associated with it. Now, when I talk about the fundamental frequency, I'm going to be talking about this guy right here. If this is a function of time, then this right here would be the fundamental period, which we could convert to fundamental frequency. Now, it turns out that how clean a musical sound looks is going to be related to how it sounds. So here you can kind of see we have this little dip there, and there, and there. And while this thing is periodic, it's not going to sound nearly as clean as a wave that kind of looks like this with far fewer dips. And within my ability to draw, I tried to roughly draw it with the same period or the same frequency. We do actually have a special name for this. We actually call this the fundamental frequency of the music, and that's going to be the sound that dominates. Now, all musical sounds, they're going to have three characteristics, and I'm just going to overview them very quickly here, and then I have a bunch of slides on each one. First of all, musical tones are going to have a pitch, or they're going to have a frequency associated with them. Bear in mind that pitch is more subjective, frequency is more physicsy, but you can use them more or less interchangeably. And what we're going to hear is we're going to actually hear the fundamental frequency or the dominant frequency of the musical note. And on the previous one, it's going to be, the one that has the biggest, so it's going to be dominated by that guy right there. We're going to talk a little bit about the intensity, which is the loudness or perceived loudness of a sound. And lastly, we're going to talk about the quality, which is going to be how many harmonics are there. And harmonics are kind of those little dips that were on the previous one. And how intense are they? So something that looks like this is going to look and sound very clear. Something that looks, kind of like this is going to look and sound less clear. Sometimes that's a good thing, sometimes that is not desirable. So first, let's talk a little bit about pitch. Again, another word for pitch could just be the frequency. And we tend to organize the pitches or the frequencies by musical notes. So A is a certain number frequency, C is a certain number frequency, C sharp has its own number associated with them. And if I was a musician, I could recite them to you, but sadly I am not a musician. Now, if we have something that is vibrating very rapidly, then it's going to produce a high frequency, and we could have a string that was really short, and what's going to happen is you pluck that string, it's really short, so it's going to go back and forth very rapidly, and it's going to have a high frequency. If we had, one of those big long instruments with a long string, then this guy is going to have a low frequency because it's not going to go back and forth nearly as fast. And when I use the word frequency, you could also be using the word pitch. Now, musicians actually give all the different pitches different letters because the numbers are kind of scary for musicians, and they actually call them A, B, C, D, E, F, and G. And actually, they say all these notes are within one octave. And after you make it all the way through one octave, then what's going to happen is the frequencies are going to start to double. And what we can kind of do is we can kind of say, okay, this is C. You kind of see the frequency is 32.7. At the next octave up, it's going to double that frequency, and then double it, and it's usually pleasing to hear doubles of frequencies kind of played together. A typical piano is going to have more than about 7 octaves or so. So how do we change the pitch? How do we change the frequency? Well, what we can do is we can just switch the size of an instrument. Something that's small is going to have a high pitch. Something that's big is going to have a low pitch. We can mess around with the tightness, and that's what guitarists do when they are tuning them. And also, we could also mess around with the mass of an object. So the thicker the object is, the lower the frequency is going to be because it has more mass and it just tends to inherently be slower. Now, something that we kind of know is we know that the speed is going to be related to the wavelength multiplied by the frequency, and the speed is actually going to be the speed of sound, 340-ish meters per second. And so what we're also kind of doing is we're messing around with the frequency, and the wavelength has to correspondingly change. So this guy right here has some wavelength, some frequency associated with it. This guy right here has a much longer wavelength and a much different frequency associated with it. Still, at the end of the day, we still have to be able to multiply those guys together and get the speed of sound. Now, something that's kind of interesting about music is most of the time it tends to be less than 4,000 hertz. We can hear up to 18, 20,000 hertz, but those sounds just tend not to be pleasing to the ear. Again, when we talk about ultrasonic sounds, sounds that are larger than 20 kilohertz, 20,000 hertz or so, we cannot hear those. Dog whistles tend to be in those range, so dogs could probably hear them, but we would not be able to hear them. And again, the older you get, we tend to lose the high end. So now let's talk about the second quality. Let's talk about sound intensity, or kind of an impression of loudness, and essentially, how much pressure is there? How much? What is the amplitude of the air that's bumping into your eardrum? If you have air that's kind of bumping into your eardrum with a small amplitude versus a large amplitude, well, I don't know about you, but the bottom one looks like it's probably going to be louder than the top one. Now, it's kind of interesting. When we talk about this, we actually talk about the intensity of a sound wave. And when we talk about the intensity of a sound wave, we're going to be talking about a number that is watts per square meter. Now, the watts, whenever you get a speaker, it's rated in watts, and the square meters is actually going to come from your eardrum. It's kind of interesting, but the human ear can hear a huge range of intensities, going all the way from 10 to the negative 12 watts per square meter. That's actually the threshold of hearing, all the way up to 1 watt per square meter. That's when things really start to hurt. So we cover huge dynamic range of 10 to the minus 12th or so in the language of intensities. Now, suppose we want to measure sound intensities. If we're talking about this huge dynamic range, 10 to the minus 12th, all the way up to 1 or even 100 watts per square meter, that would make your ears bleed, by the way. We're talking about 10 to the 12th, 10 to the 14th dynamic range, and people tend not to like that when it comes to measuring these things. So we actually have a logarithmic scale that's called the decibel scale, and that's actually going to be a sound level or a sound intensity level. Essentially what we do is we set the threshold of hearing to be 0 decibels, a dB, and then for every factor of 10 we go up right here, we just go up by 10 right there. And there's some big nasty logs kind of going around behind the scenes, so you can kind of see that this guy here went up by a factor of 10. This guy right here goes up by a factor of 10. This guy right here goes from 10 to the negative 12th to 10 to the negative 8th, so it goes up by a factor of 100. So right here we go up by 20 dBs. All this scale really allows us to do is to be able to cover this huge dynamic range of what we can actually hear. Now, one thing to kind of just tuck away into the back of your head is the intensity of sound that you hear is going to be entirely dependent on your ear. So it's going to be depending on more of a physical attribute than a mathematical one. So someone that is hard of hearing is going to hear sounds slightly differently than you are. So how loud something is actually a little more of a physiological sensation. And bear in mind that the ear does sense some frequencies better than other ones. So let's just get a little bit of practice of this. How much more intense is it to go from 80 dB to 90 dB? It's actually going to be 10 times as intense. Suppose I wanted to go from 80 dB up to 100 dB. That's going to be 100 times as intense. If I wanted to go from 80 dB up to 1,000, let's do 120 dB. That's 40, so it's going to be 1, 2, 3, 4, just like that, in dB.